Okay. So what was the first thing we talked about in this unit? The very first thing, and so far the only thing we talked about? Work. Okay. And work is always the, I don't want to say the easy, but definitely the short concept of the unit. The big concept is always going to be energy. So, first of all, what is the definition of energy whenever you talk about it? Okay. So, if you have more energy, you can do more or less work. If a system has more energy, there's more work to be done, which means energy, the easiest way to define it is that it's the capacity or the ability, but the official word used in most textbooks is capacity. So it's the capacity to do work. More energy, more means more, potentially at least, potentially more work could be done. If no work could be done, that energy basically will be stored until work needs to be done. Okay. Now, the thing about energy is there are many forms, or it comes in many ways or shapes, okay? But they call them forms. That's why they call it energy what? Energy transformation. Trans in Latin means to go from one thing to another, and form just means shape. So transformations means something that actually changes the shape. So there are many forms of energy, depending on what? Depending on how complex the situation gets. In a similar way, how many forces are there? Well, so far we've covered how many? We've only covered how many in the forces unit? 5. We've covered Fg, Fn, and so on. The more complex the system gets, probably the more forces you need to be aware of. Same thing with energy as well. Okay? So the first thing we're going to do is exactly the same handout or worksheet we did in 3U, which is basically like a quick matching exercise. Okay? So what I want you to do here is this. Okay? This is the exact same handout that you have. Okay? What I want you to do is basically look at the expressions or the names on the left-hand column, and look at the definitions on the right-hand column, and tell me basically, again, you do it, I'll give you 5 minutes for it, tops. You choose which ones here match with which ones here. By the way, if you do a quick count, how many types of energy am I giving you here? How many do we have here? Come on. How many do we have here? 10. How many definitions do we have here? More than 10 or just 10? We have 13. What does that tell you? Actually, no. But okay, that could be. Some are wrong. But actually, no. All of these are correct. So that only leaves one explanation for why there's 13. Say again? Exactly. Some of those definitely can mean multiple ones of these. So go ahead. Okay, let's start. All right. So the way, listen up, pencils down until you want to correct things. The way I'm going to do it is, instead of asking you, what do you choose for this one? I'm going to start from here. So what did people choose for internal motion / vibration of particles within matter? Just raise your hand. What did you choose? Okay. So Ahmed, what did you choose? You chose sound. How many other people chose sound? Okay. So Ammar and Maha chose sound. Okay. Who else chose something else? Come on. There's no way everyone chose sound. Who else chose something else? Come on. Raise your hand. What did people choose? Come on. There's no, you know me, there's nothing wrong with getting the incorrect answer. That's fine. That's the whole idea of doing this. Come on. Hamad, what did you choose? Sound as well? Okay. Who else chose something else? Random guess. What'd you go for? You took radiant energy. Okay. Who chose kinetic? Why did you say so? Okay. Why did you choose kinetic, Hussam? What was the keyword in that phrase that made you think, you know what, I'm going to go for kinetic? My vote goes to kinetic. Motion. Does that make sense? Of course it makes sense, because motion is what? Motion means what? What was the first unit we did in this course? Kinematics, right? Here's the thing. That was the trick in this one. Motion actually, Hussam, motion actually tricks you into thinking the incorrect one. Here's the thing. Technically, anything that moves has what kind of energy? No, anything that has what? Has kinetic energy. But actually, this one is not kinetic, and it's not radiant, and it's not sound. Would anyone like to take another guess? I'll give you a hint. If you actually have particles vibrating a lot in a liquid, what does that tell you about the liquid? What is high about that liquid? No, it's hot, which means it's what? Thermal energy. The definition of thermal energy is the internal motion, especially this word. What's this word? Vibration. Vibration, okay? Whenever you talk about the internal motion / vibration of particles within matter, that's the definition of what? Which one? Thermal energy. And by the way, just so you know, thermal energy is the only energy of an object that could never go to what? Zero. Why is that? Absolute, like to 0 joules. No way. For one reason. Can you ever completely stop particles from vibrating in any material? Absolutely not. Absolutely not. Particles, electrons, protons, and neutrons are particles that need to be moving to have what? To have mass. Which means if you stop them moving, they stop having what? And then you get them. What's the most famous equation in science? E equals mc squared. If you stop not quantum, a subatomic particle from vibrating, it completely forfeits its what? And it completely turns into what? Energy. Does anyone know what's absolute zero? How many people have heard of absolute zero in chemistry? What is absolute zero? Okay, so we have 3 scales of temperature. The two that we're most used to are what? Celsius and Fahrenheit. But what's the scientific absolute scale? It's in what units? Kelvin. And by the way, never say degrees Kelvin. It's very common because you say degrees Celsius, degrees Fahrenheit, so you just also keep saying what? No, there is no degrees Kelvin. It's just what? It's just Kelvin. So it's called absolute zero or the absolute temperature scale because the lowest temperature in the universe is what? Is what? Zero what? 0 Kelvin. Does anyone know what's 0 Kelvin? In Celsius temperature. It is the coldest temperature that a material could exist at and still have mass. Does anyone know what? By the way, it's a super cold temperature. Guess a number. Obviously, it's negative. Go for it. No, it's a bit higher. Not 3. No, higher as in it's less negative, like closer towards the 0, up. If you imagine a vertical scale, so it's not that here. No, it's above. Anyone knows this number? You hear it a lot if you do grade 12 chemistry and you do a lot of gas temperature and you convert from Celsius to Kelvin. You use that number. Any? Negative 273.16 in what? In Celsius. This is the, by the way, it's not exactly 16. It's a very precise number, but I just remember it from my chemistry days and physics days to 16. What happens if a particle reaches that exact temperature? It completely stops being what? It completely stops having what? Mass, and it purely turns into what? Pure what? Pure energy. What's the only particle in the universe that has no mass? Pure energy? Photon, light, or in general, not just visible light, all of electromagnetic waves, radio waves, X-rays, infrared, all of them are carried through what particle? Photons. And once you completely reach this, you forfeit all of your mass and you become what? You become what? So far, I think the lowest temperature they were able to get in an experimental setting is 1. What does small n mean? 1 nanokelvin, which means what? The 0 Kelvin, they were able to get what? Particles to vibrate so little, but still actually what? Vibrate. But they vibrated so little such that the temperature in the environment was how much? 1 what? 1 nanokelvin, which is almost what? But not quite 0. Do you see what I mean? How did they know that they couldn't go any lower? Because when they lowered it, they couldn't see any more particles. All they could see was what? Was pure bursts of light. Which means what? All of the mass of those electrons, they cooled down electrons, turned into what? And they won the Nobel Prize for that, I think in the year 2005. Okay? So again, the only energy in a body or in an object that you could not bring down to 0 is which energy? What was it? What was the internal motion vibration? Thermal. Because once your temperature goes to absolute 0, you have no more thermal energy, which means you don't have mass anymore. You are yourself just pure what? Pure white, pure light. Okay? Always remember that. Thermal energy is the only energy you cannot bring to 0. Okay, so that here, let me just go. That's B. Okay, what did people choose for motion of electromagnetic energy in? Some of you have heard this word. Who can say it? Transverse. Where did you hear that word before? In physics or math? You will mostly hear it in math when you talk about sine and cosine wave. Who would like to tell me what they chose for this one? Come on. Josh. That's what? How many people chose radiant energy? How many people chose something else? Come on. What did you choose? Say again. And you know what? You're right, but not the what? Not fully right. Because remember, radiation, what's another name for radiation? What does EMS stand for? EMS. And not emergency medical services. Come on. What's EMS? In science. Electromagnetic. No. What do you call a range? What's the scientific word for range? Starts with S. What do rainbow spectrum. What does spectrum mean? A range of continuously what? Changing values, right? Like something is on the spectrum, it means it has a range from here to here. So that means motion of electromagnetic energy in transverse waves. Okay, question for you. You said you chose electric, right? Why didn't you choose the second part of the word, which is what? Do you see what I mean? You either choose none or both. What's the word that combines both? Radiant energy. Everyone, this is the radiation. Radiation is motion of electromagnetic energy in transverse wave. Okay, how about this one? Motion of energy through matter. What is that? Ahmed? That is sound. Everyone, that is sound. And by the way, just so you know, depending on the kind of matter, it has a different name. If it's in air or in gas, you call that what? You call that sound. If it's in solids, if the vibration is in a solid, you call it what? You can call it solid waves, ground waves, shock waves, like geophysicists do when they discuss earthquake. What's the remaining state of matter that I didn't talk about? Liquid. Whenever it's water or liquid, you just call it what? Liquid waves. Okay, like tsunamis, for example. Okay, but in general, it has to be through what? Can you ever hear sound in space? Boom. Whenever you're going to a sci-fi movie and there's an explosion in space and you can hear it, go out, ask for your money back. Because you can never hear what? Sound needs what? What does sound need to go or propagate or travel? It needs a medium. Medium could be what? Solid, liquid, or gas. Okay, so always know that through matter means it has to be a what? A sound wave in general. Okay? Oh, we're going to cover, who can say this word? Longitudinal. Okay, again, we're going to explain what it means when we do waves in a couple of weeks. Okay, no surprises here. Energy of motion. That has to be what? Any object in motion possesses what? Kinetic energy. Done. Good. Okay, energy form that's either visible or invisible. And by the way, who's making the decision if it's invisible or visible? Us, humans. Like we can see or we can't see. By the way, can we see the same thing that cats see, for example? No, because we have what? Different eye structure. So we always say if it's visible to us, we call it visible. If it's invisible to us, even if it's visible to cats or bats or so on, we still call that invisible. We are the most important ones. What do you call that? What's energy form that you either can see or you can't see? Any takers? Yeah. Ammar? It is radiant. It's also a what? A form of radiation. What's the only part of radiation spectrum that we can see? See, that's why I don't like to call it just light. I call it what? Visible. No, visible light. Because, okay, who remembers the weakest kind of electromagnetic wave? Like the weakest. Say again? Come on, man. X-rays. They cause cancer, right? Because they're very energetic. What's on the low, weak end? No, even lower. Infrared are weak, but there's even weaker. Come on. It's outside in towers. Radio waves. Radio waves are the weakest. Radio waves are the weakest. Okay, what's the next stronger one? I'll give you a hint. You use it to heat food. Microwaves. Microwaves are the next stronger on the list. By the way, can you ever see radio waves? Do you see waves coming out of radio towers? No, which means to you it's what? Can you ever see microwaves as you heat food? Which means also to you it's what? Invisible. Okay, what's the next stronger one? You said it. Infrared. What does infra mean in Latin? Above or below? Infra. When we talk about infrastructure, infra means what? Infra means above or below? The base. That's why they call something inferior. Inferior comes. What's the opposite of inferior? Superior. Inferior below, superior above. So that's what we call subsonic, supersonic. Sub means what? Like sub-zero. Supersonic means above. So infrared means what? Below which color? Sorry, not that. Below which color? Infrared means below red. Okay? Can you see infrared? No, you can't. But do you know it exists? Yes, you do. So that's another one of what? Invisible. Okay. Now what's after infrared? Exactly. The visible. Does anyone remember the acronym from grade 10 science for the colors? Roy, G, Bev. Red, orange, yellow, green in the middle, blue, indigo, and finally what? Violet. Which means if there's infrared and then you get Roy, G, Bev, what's after V? What causes skin cancer if you don't, use protection? Ultraviolet. So now we're talking about the low energy or the high energy ones? High energy ones. So ultraviolet is high energy. Again, can you see it? Can you see ultraviolet coming from the sun? No, you can't, but you know it exists. Okay. What's the next stronger one? You said it. X-ray. X-ray are stronger than what? Ultraviolet. Okay. What's the strongest of all? The gamma rays. Gamma rays come from what? Nuclear decay and nuclear explosion. So all of these are what to us? Except for what? They're very visible. And just so you know, the only wavelength your eye can detect, like your cons and rods can actually be fired if light falls on it, your eye is not equipped to see anything beyond this range. What does NM mean? Nanometers. If the wavelength of light is bigger than 700 or what? Smaller than 400, your eye can see it. You can feel it as heat, but your eye cannot actually what? See it. Do you think other animals could see things outside of this range? Of course. See, that's why I don't like the word see. I like the word detect. Because detect is a more what? Neutral way of calling everything as a machine, right? Detect. Bats detect. Cats detect. We detect. But when we detect, we call that what? See or vision. Make sense? That's why. Bats okay. Can bats see? According to us, no, they can't. But yet, they hover very well among trees. How can they do that? Exact. Echolocation. Echolocation. They basically send a sound wave, a supersonic wave, and it comes back and it detects what? Distance and speed, and it just goes. Do you see what I mean? Like a hugely, amazingly sensitive system. Your eyes cannot detect anything. Anything more than that, is what? Is what? Infrared. Anything lower than that is what? Ultraviolet. Okay, we're going to discuss that a lot when we talk about light. Okay, all right, so that's what? That is radiation or radiant energy. Okay, come on. Energy due to stretching, compressing, or twisting, or deformation energy, when you change the shape but not the mass. Like when you do this. Easiest example ever. This is what? Elasticity of an elastic material. Perfect. Energy, keyword, stored, still stored in the bonds of molecules. Like when you eat food and it hasn't been broken yet. How many people did organic chemistry here? What are the most important molecules in organic chemistry? What do you call them? Hydrocarbons. What does hydrocarbon mean? It's a long chain of mainly what two kinds of atoms? Hydrogen and carbons. Okay, the building blocks of life. C, 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 and you got the what? The H. That's exactly what Mr. Mitrovic is teaching, right? All of these bonds. As long as these bonds are not broken, hey, what's up? No, go ahead. Yeah, yeah. No problem. Thanks for letting me know. As long as it's not broken, energy is still what? So what do you think that is? Josh? No, no. Okay. You're right in nuclear still being stored, but it's the wrong location. Amar? Chemical, yes. As long as it's stored in the bonds of what? Molecule, long polymer molecule, that's still chemical. Okay, so that's chemical. All right. How about the energy stored in space between two magnets? When you leave it, they either go in or go out. What is that? Yeah. It is magnetic. What did you want to say else? Okay, so you know that once you release two magnets, they either move what? Closer or? So once you release, it becomes what? Once you release it. But before you release it, and you're holding the system intact, what's in between that's about to be used? Do you see what I mean? As long as it's stored, it's any of these except what? Except everything stored is any of these. Once you get released, it becomes what? Kinetic. So what would it be? Magnetic. Magnetic is stored between until you leave your hands, and then they either move away or move in. So that's magnetic. Okay, come on. This one has the keyword hot. Thermal. Energy that makes objects feel hot, which is basically the temperature or thermal. Energy due to elevation above the surface of a planet. That is the only thing pulling it down, which is gravity. Perfect. So that's gravitational energy. Okay, energy from the sun. Technically, the sun gives so many, but if you collect them together, what does the sun mainly give us? Light and electromagnetic waves and all of that. So it's another form of radiation. Yes. Yeah. Well, okay, but the main one is, by the way, thermal is just another manifestation of infrared spectrum. Yes, or infrared part of the spectrum. Sorry. Energy due to motion of electrical charges, like when you connect something to a socket. It's gotta be what? Electrical. I mean, we're doing process of elimination here. We're almost done. Finally, energy still stored in the nucleus before you break it apart. That's gotta be what? Nuclear energy. And mainly, those are all the kinds of energies that you'll ever deal with, at least in in an undergraduate physics or engineering setting. One more comment before, almost done anyway. One more comment before I jump to the next slide is, by the way, all of these energies, everyone, all of these energies in most physics textbook, they have another name next to the name of the next to the name of it before the word energy. Potential. All of these energies could be called what? Except for one. The only energy that is not, by the way, when you say you have potential, does that mean it got released yet, or is it still stored? Which means all of these are potential. Electrical potential energy, elastic potential, you haven't, let the system go yet. Gravitational potential, I have not let go yet. Nuclear potential, it's still stored. You haven't broken down the nucleus yet. Radiant potential, it's still in the waves themselves. Sound potential, it's still in the what? In the actual layers of the air. Magnetic potential, chemical potential, thermal. The only one that's not potential is what? Kinetic. Once you start setting things in motion, are things being stored or are they being used up? That's it. The only energy that is not potential is what? Kinetic energy. That's why I never like to call them potential, because we know they're all potential except for one. Okay? I never call it potential. They're all potential except for kinetic. Okay? So always remember that. Once you start moving, that's it. I don't have potential anymore. I'm burning up my potential. I'm using it up. I'm expending it. Okay? All right. Okay. Any guesses for the physical symbol of energy? And it's exactly what you're thinking about. Why uppercase, not lowercase? But what? Okay. But why is it not lowercase? Mm-hmm. Lowercase in general is always for what? For electrons, which is usually the charge of an electron. Okay, which we'll cover in electricity and magnetism. So it's always uppercase E. What can you tell? Vector or scalar? Of course, scalar. I mean, let's think about this for a second. Everyone, does this have thermal energy in it? Thermal. What did we say? All objects must have what? Because all the particles inside are what? Vibrating and moving. Okay? If I turn it this way, does the thermal energy change? Which means, is it direction dependent or independent? There you go. Energy has no direction. Done. Energy is just an amount of what? Of work ability stored in the object. It must have no direction. Okay? All right. What is the unit for energy? Same as work, which is what? Joules. Yes. Capital J. Absolutely. So that tells you there must be a relation between energy and work. And there is actually a very important one. Okay. What is the relation between work and energy? What is the relation between work and energy? It's this. Work is defined to be the change in energy of an object. Work is defined to be the change in energy of an object. Question back from kinematics. What's the symbol for change? Delta. Nice. So now we can actually come up with a what? With an equation, which is this. Work is equal to delta E. And what's the expanded way of writing delta? Always. What does delta mean mathematically? Always. Final minus initial. Okay, so let me ask you a question here. And that's going to be the last thing we talk about today. We're going to finish the rest of the note tomorrow. My question is, what three possible cases could you have for that subtraction? What's the first case? Again, those are two numbers, so they always have three cases. Ammar, give me one case, because we're going to say the case and interpret what it means. Mhm. Oh, you're right. I'm just talking about what are the possible outcomes of this equation. That's all, without any physical, without any physical explanation. Go ahead. I mean, you have EF minus EI. You're subtracting two numbers together. You still don't know what the numbers are. What possible cases could come up? Absolute zero. What does that mean? Everyone, if EF minus EI is equal to zero, what's the only meaning of that? That means E initial and E final must be exactly what to each other? Must be exactly equal and the same to each other. Which means then the initial energy of the system and the what? And the final energy of the system are what? Are zero. Which means how much work was done on the system? Zero. Because the system kept its own energy the whole time. By the way, just so you know, it just means that initial and final are the what? If okay, everyone, if I tell you I have $100 right now, tomorrow you ask me how much money do you have, Mr. Ramadan? I'm like, still $100. Does that mean I did not spend anything for 24 hours? What could it mean still? I spent, but also what? Gain. So overall, my net gain, or sorry, my net change is what? So you just know that the system started and what? Ended with the same energy. Can you tell what happened in between? No, you can. But you know that whatever happened in between went through as much loss, as much what? As much gain. That's all you know. But you know that basically the whole thing balanced itself. Okay, that's case number one. What's case number two? Ahmed. Say again? If it's positive, what does that tell you? Which energy is bigger? If that, the final, which means what? Did the system lose energy or gain energy? Which means what? Did you take energy from the system or did you supply energy to the system? You had to supply because it had to end up higher at a higher. By the way, does this, everyone, does this seem like something you did in chemistry? Higher energy, lower energy after a reaction. What is that? Exothermic and endothermic. What's an exothermic reaction? Exo. Which means what? Did the system keep its energy or lose some of it? Which means what? Which energy is more, initial or final for an exothermic? For an exothermic, it lost energy. So which energy is higher, after or before? Before, which means what? EF minus EI is negative, which means the system did what? Did negative work to lose energy. How about an endothermic reaction? What does that mean? Did it lose or did you need to pump energy into it? You needed to technically most of the time heat it up or stir it to add energy to it to get the what? The particle mixing and go above a transition energy state to be able to what? To combine and react. Then you know what? Which one is bigger? Which one is bigger for an endothermic? Because energy initial was not enough, so you had to pump some in to get a higher EF. Okay? So again, that's why one of the, like the people who do chemistry, a lot of thermodynamic reactions, study a lot of energy transformation. They need to, otherwise you have no idea how to interpret the system.